哦，你们有PS 还是那个哦，PS 的。
Okay, hello. I think we are going to start. Okay, so welcome to this third table. We will be discussing about privacy preserving AI. I think at this point we all understand the potential of AI, and we can imagine also its increasing relevance and impact in the coming years. AI will be everywhere, from healthcare to transportation, from our everyday gadgets to our workplace. Actually, to make this introduction, I use ChatGPT. So, but we also know that to get models, we need data, and we are the ones generating this data. So it's our preferences, our interactions, what shapes the models we use. And we also know that we cannot run these models in our mobile device because they are massive. They have to be put somewhere in the cloud, and we have to submit our queries to the cloud to use these models. So it looks like in order to have AI, we have to give up on privacy. But it's not true. We can actually have AI and privacy at the same time if we use privacy-enhancing technologies. And there has been a lot of research on this in recent years, specifically on secure multi-party computation, and fully homomorphic encryption, on trusted execution environments. And we have the luck of having with us 4 experts on these topics. We have Ilaria, that is expert on FHE. We have Daniel Quinn, it's called Quick. Okay, it's good enough. Expert on TEs. We have Daniel Escudero and Marcel Keller, experts on MPC. Of course, there is a lot I could say about them, but I would prefer them to introduce themselves. So if you can give us like a brief introduction of your career, who you are, and please don't be humble. Brag as much as you can.
Okay, hi everyone, nice to meet you. My name is Ilaria Chillotti, and I'm a director of cryptographic research at Zama, which is a startup based in Paris. And in Zama, we develop fully homomorphic encryption, which has been kind of my specialty since I started research. And I take care of doing research in homomorphic encryption and try to improve not only the algorithmic part, but everything that is around cryptography, of fully homomorphic encryption, like parameter search, optimization, and so on. And that's it.
Okay, and you are also one of the main authors of the FHE scheme.
Yes.
Yeah, I think they already know you, but
okay. Well, maybe
just
didn't come this morning, maybe.
Maybe new people.
Okay, so hi everyone, I am Daniel Wynn. I am the CEO of Meter Security. We are a startup that focuses on using hardware-based solutions to provide AI models with privacy guarantees. For instance, we deployed the first solution to serve AI models on Intel GX, and we were able to run like pretty large models with a high level of privacy, who have been audited and so on. Our code is open source. And yeah, overall, we're focusing on providing both privacy guarantees for data that is sent to AI providers, but also transparency, because hardware-based solutions have integrity as well of the code that is executed. But yeah, our overall privacy and transparency in the AI.
Thank you. So, hi everyone, I am Daniel Escudero. I'm currently a researcher at the JP Morgan AI Research working on cryptography. Prior to this, I got my PhD from Aarhus University, where I worked on cryptography topics. So I mostly work on research, both from ranging from theoretical topics to practical topics, mostly confined within the MPC domain, making MPC more practical for certain applications, or also general purpose MPC. Have co-author works with Marcel Keller, for example, here on privacy preserving machine learning, and also some theoretical works on lower bounds and different theoretical aspects well of MPC. So looking forward to the discussion.
Hi everyone, my name is Marcel Keller. I work for the CSRO in Australia. I should also say that the views I will present here are my own, not theirs. I work, as Daniel mentioned, I work on privacy preserving machine learning. And I guess my biggest claim to fame is the MP-Speeds framework for secure multi-party computation that I have used to implement a variety of PPML algorithms.
So thank you. So as you can see, we have experts on FHE, MPC, and TEs. And they have hands-on experience as well. So they have developed products, libraries. And you have, like in Zama, you have concrete. Daniel Quinn has a blind box in Meter Security. Marcel Keller, as he mentioned, he developed a very well-known general purpose MPC framework that is called MP-Speeds. So the idea in this table is to discuss what these technologies offer, how they can be used to provide privacy in machine learning, what are the differences between them, the main challenges, trade-offs, and the future directions in order to accomplish market requirements. I would also like to point out, because I got this comment before, that not all the technologies that we can use to provide privacy in machine learning are represented in this table. Like there is also synthetic data, and there are also new techniques based on signal processing, but this event is about cryptonodes. So we are representing here cryptographic techniques. And also, I tried to bring an extra panelist, expert on synthetic data. It was impossible. Everybody has holidays in August. Only cryptographers don't. But thank you for being here. Thank you for making the effort to come into our affiliated event. I have been checking your papers. So I have a list of questions that I would like to ask you about your papers and your written work. But I would also like this to be an open discussion. So whenever you feel like sharing your opinion or you have a different opinion, you don't agree with anybody's comment, just feel free to comment on it. And this also extends to the audience. If you want to make a question, just ask Amanda for the mic at any time, so you can interrupt us and make the question. So I think to start and to put everyone in the same page, it will be convenient to define what these technologies are. Normally, when we talk about MPC, FHE, or TEs, we say that these are technologies for computing over encrypted data. But when we look into the detail, this word encrypted means different things. Like it can be encrypted, it can be secret sharing, it can be making the computations inside a box that nobody can access. So I would like you to give us like a more accurate definition of what it is and how it can be used for machine learning. And maybe Laria, you can start with.
Okay, so fully homomorphic encryption, or I will often call it FHE, is, well, as you kind of said, is a technology that allows you to do computations over encrypted data, which means that you encrypt your data, and once it's encrypted, you can perform computation, and the result is going to be the result of the computation you do on the ciphertext in practice. So if you want to do an addition onto encrypted message, the result is going to be the addition of the two original messages, multiplication as well, or more in general, different functions. But just to make an example, it can be used like for many, many applications, in particular machine learning, as we're discussing in those panels. So imagine, I don't know, that you have some sort of DNA sequencing or your genomic data, your RX, some blood tests, and you want to use machine learning to classify this data to discover if in your DNA there is a mutation, if you have a certain disease. So what you're going to do, you're going to take your data, you're going to encrypt it by using homomorphic encryption schemes. You're going to send it generally to a cloud provider that has the model, and they are going to perform the computation, so evaluate this model on top of your encrypted data. And they will never see what is what is inside the encrypted data, so they will perform the computation by not seeing what they're computing on. They will send you the answer, and you, as the person that generated the secret key, are able to decrypt and to discover the answer. So again, during the entire process, the data is never revealed, is always encrypted. And we can do this stuff nowadays. It was kind of a dream a few years ago, but now we have very, very nice solutions. And all the solutions that we have that mainly used are based on LWE, the learning with error problem, which is also used, probably you heard about it, in the NIST post-quantum competition. Many of the solutions coming out from this competition are based on LWE. And yeah, FHE schemes are based on this. So this is very huge summary of what FHE is.
Okay, in our case, we use hardware-based solutions to protect data while it's being used by other parties. So an example is similar, like imagine I am OpenAI, you want to use my GPT-4, but you don't trust me with your data. The idea would be that there are some hardware solutions that you can find in cloud providers. For instance, the next Hopper, the H100 from NVIDIA, has secure enclave abilities. And so how can I analyze your data as OpenAI while providing you guarantees that I don't see it? The idea is that on your side, you will encrypt data and send it to me. I will put it inside the secure environment. It's decrypted inside. So I guess we cannot say we're officially end-to-end encrypted, but we'll be end-to-end protected. And I will explain why. But the data is decrypted inside. while it is inside, it isn't clear. You can perform operations, you can apply the AI model inside. And the idea is that while it is inside, there is hardware isolation and or memory encryption, so that not even software admins from OpenAI can read users' data. And so, but because it is in clear inside, it's much faster. We're not using fancy data structures and so on. It's regular stuff. Therefore, it's very fast. We see that there is a slowdown from 0 to 20% with secure enclave-based solutions, which is quite interesting because, like AI requires to be relatively fast for a good experience. We would not like GPT-4 to be 10,000 times slower. I guess it will not be great for your experience. And that's possible with that kind of solution. And so after you have done the computation inside a secure enclave, you re-encrypt the output with the keys of the customer and you send it back to them. So that's why it's end-to-end protected. It comes encrypted but isolated, and then it goes back encrypted. So that's why I say it's end-to-end protected. But with that, we have done a lot of experiments. We are able to have something that is fast, private, and easy to use both from, let's say, OpenAI's perspective and from the end user perspective. And for instance, we're actually going to deploy the first end-to-end protected chat where we'll deploy a Llama 2 70 billion with that kind of secure hardware so that people can consume a chat GPT-like interface where they have nothing to deploy on their phone or whatever, except some modified TLS solution, and still they benefit from a state-of-the-art AI system with privacy guarantees.
Okay, thank you. Any of you can choose.
Yeah, so in terms of MPC, the name stands for multi-party computation or secure multi-party computation. And the setting is, maybe one can phrase it as a generalization of FHE in a sense. So you have, let's say, two parties, Alice and Bob, and they want to compute a function. Each one of them has a private input. Maybe one of them has a model and the other one has an input to the model. And then the function is the one that takes the model and the input and evaluates the input of that model. So in MPC, in contrast to FHE, we allow for interaction. So Alice and Bob can interact in multiple rounds, possibly many rounds, possibly dozens of rounds, hundreds of rounds, thousands of rounds, until they eventually get an answer, the output of the function perhaps, without leaking anything else about the function. And it's not only about two parties, it can generalize also to multiple parties, or you can have 10 parties, each one of them having an input. Maybe it's a population of 10 presidents trying to vote some decision or something similar. And in recent years, I would say there was this very cool idea because in MPC, the way that there are different forms of MPC. For example, you have garbled circuits, but you also have secret sharing based MPC. And the way that it works is that at the beginning, everyone will secret share their input, which is a form of encryption, if you will, in which different pieces leak nothing about the secrets, but enough pieces together will completely determine the secrets. Everyone begins by secret sharing their inputs, and then somehow the parties jointly go through the function, the specification under a certain protocol and obtain the output. So because of this layout, there is this idea of outsourced computation or a client-server model where multiple clients, not only the ones running the MPC execution, multiple clients can provide secret shares to some servers who are going to execute a protocol on their behalf. And I think this is what some literature considers. Maybe Marcel can expand on the client-server model, but I think this is the difference with encryption and secret sharing. There you are delegated to some servers who you're assuming they're not colluding. In encryption, you're really encrypting, and nobody who looks at this encryption without the key can decrypt anything about it.
Yeah, thank you, Daniel. So I think you already introduced MPC. I think I would like to provide some abstraction. I think what all these technologies have in common is that they provide some sort of black box where there's something happening inside the black box, like computation is happening inside the black box, and the data only comes out, some results only come out at the very end, and nothing gets revealed when it goes, once it's inside and when the computation is on the way. Now, how do these three technologies differentiate is like basically what makes the walls of the black box. So you have FHE, where the wall is this encryption algorithm that still allows this operation. So the wall there, if you will, is basically the cryptography, the mathematics that underlie it, whereas with TEs, the wall is the hardware and and the fact that actually the chip barriers are all sort of are correctly engineered. And then last with MPC, basically the wall is a bit harder to define because it's based on the secret sharing. So basically the black box is kind of run in an abstract manner between the parties that participate in the computation. And what makes the black box is that that the information inside is split up like this, like in sort of like a puzzle way, but mathematical puzzle way that we call secret sharing.
Excellent. Very good definition. I also think that to fully grasp the difference between these technologies, it's very important to define the trust model. Like, who do we need to trust? Like, for example, when you were defining PEs and FHE, it look like the same. Like, we will have the client and the model owner, but actually it's a little bit different between FHE and PEs. In FHE, it's clear, no? Like, you have a client, I want to process my input privately, I encrypt, I send, I forget. I repeat the output and I decrypt. I don't need to trust anybody.
Yeah, that's a little bit the idea. But so in general, the main use case is you're the user and you send, as you said, your data, and then the computation is going to be done. So your data is protected all along the computation. So even if you don't trust the owner of the model, the person that is doing the computation, your data is going to be protected all the time. But sometimes we can like move a little bit perspective and think about the fact that maybe the user might be instead malicious, and what we want to protect is instead the model on the other side. So actually there are several trust models that we can take into account, and I think FHE, but also the other techniques propose solutions for all of this.
Yes. Yeah, well, I was actually planning to go to the other side, not only the client side security later in another question, but yes. In TEs, one of the main problems that in literature we see frequently is side channel. I had the opportunity to discuss this with you over an email and explain me that in order to not care about side channel attacks, your trust model actually considers three parties, like the model owner, the client, and then the hardware provider, in which you actually have to trust. So that's the main distinction between FHE and PE.
Yeah, so I guess it's easier to understand with a real scenario. Let's imagine you have OpenAI, that you don't want to trust them, but you want to use their GPT-4. You have Azure, who is an infrastructure provider of OpenAI. And then at the lowest level, there's NVIDIA that provides these confidential GPUs. And you are the user. So there are four parties. And so the truth is, and that's something we might not say out loud, is with hardware-based solutions, you have to trust the cloud providers. And because potentially you can do physical attacks, or they could, for instance, there's a mechanism called attestation, where you have to provide some software to prove that you're talking to a secure enclave and so on. And at least at my company, we've chosen to say upfront, okay, secure enclaves reduce the exposure to cloud providers, but you still need to trust Azure. And of course, you still need to trust NVIDIA that they do the work properly. However, what you gain is you can totally remove OpenAI from the equation. With solutions like ours, you can guarantee that OpenAI does not see your data. You still have to trust Azure that they do their work properly, but I guess a lot of enterprises, even banks, trust Azure. But that's still a big hypothesis. But TEs allow you to use OpenAI, for instance, GPT-4 and so on, without having to show your data to them in clear, as it remains isolated, even from their software admins. So that's the way we operate with TEs.
Yeah, thank you. And maybe for MPC, it's a little bit more difficult to define the trust model, no? Because you have different settings. You have like honest majority, dishonest majority. You have also different security models, active, passive. So could you give us like a brief explanation of these setups?
Yeah, so like to be bluntly, it's like MPC is better and worse than the other two at the same time, because like better in the sense that there are more options, like with different trade-offs. So like you can say, yeah, it's okay if like, you know, just some of the parties in the computation are trustworthy, or we have like a higher requirement, which then gives us like faster protocols. Victor also hinted at the important differentiation between like a malicious security model and the semi-honest security model, which basically the latter one, the semi-honest security model, says that yeah, we trust the parties, like not completely, but we trust them to follow the protocol. So they are given instructions, and we trust them to follow the instructions. But whatever they see in the course of executing these instructions, they will try to derive information. So that's sort of the way that we don't just give anyone any information. Whereas like in the malicious security model, we at least have some checks on the parties that participate, and if these checks fail, we abort the protocol, or there's even more flavors. We can actually recover from parties failing to adhere to the protocol. But I would also say that I think like one thing I would like to bring up here is like sort of like when you think about kind of like the client server model, in sort of like the FHE case, you pretty much subscribe to the two-party model, because if you can see encryption, including homomorphic encryption, like as a two-party secret sharing, because like someone has to have the key and someone else has to have the ciphertext. And of course, you bring them together, you get all the information. Whereas like with secret sharing, there's like all these different levels and possible, and that also sort of like enables in the client server setting, basically that enables like a lot of clients just have to trust like one or two of the server parties for the security to hold up.
Thank you. Yeah, you made a valid point there. Something that I also wanted to ask. When we talk about FHE, about the trust model, it is clear who are the parties: client, model owner. When we talk about this, it's also clear, like model owner, client, and then we have the hardware providers know-how. When we talk about MPC and we go to a paper, we talk about numbers. 5 parties, we can trust 1. N parties, we can trust 3. But when we have to implement that in a real scenario, we have to choose which parties have to reconstruct the secrets. So how do we choose that? And how is that communicated in a real environment?
So the first thing is that MPC allows for 2 parties as well. So you can have 2-party inference, 2-party training, and you have these variants that do exist in the literature, and they are faster than FHE because they leverage interaction. So if you are in a setting where you can pay for interaction, you can have many rounds. The 2 parties are not that far from each other, and they are relatively constrained computational resources. You can implement indeed 2-party computation solutions for this. Now, in the context of multi-party, where you have different parties who want to compute, it is true that most of the time we have an input owner and a model owner. And what we typically do is we say, okay, let's say we have 3 parties who are willing to provide, let's say, an inference service. So this happens, for example, Mozilla. This is a good example with the Prio use case. So they wanted to offer a 2-party inference service. I mean, not inference in the sense of ML, but like statistics service. So they partner with other nonprofit organizations that advocate for privacy. And then if you believe that these 2 organizations are not going to collude, then you trust that whatever data you are inputting to them in secret share form is going to be secure. So I think this is the type of settings when, let's say, we write our papers and when we motivate this domain of MPC, we think of a setting like this where you have, I don't know, just making up names. You have Meta here, Microsoft here, Google here, who somehow agree to provide a service under certain fees, perhaps, where you just input your data in secret share form, and then they're going to compute on them. And as long as you trust that two of these companies are not going to collude to steal your data is going to be safe. So I think this is the multi-party version of that.
Yeah, I would also add to that this is I would argue, the most practical scenario, because of the resources like involved to set these things up, because the sort of the advantage of MPC compared to FHE, I would say that you can run these like deeper and bigger computations, but it comes at the cost of more interaction. So the policies have to be online, throughout, and for like, like even tasks that in AI sound like ridiculous, it still takes a good deal of resources in MPC. So you need to have like a certain setup. So I personally would envision that MPC is exactly run by a bunch of large organizations whom the people whose personal data is involved like do have at least some sort of partial trust in some of them somehow.
Thank you. Very clear. I have another question. We are talking about privacy here. No? These technologies allow a client to send private input, obtain a private output. But what about correctness? How does the client know that his private input was processed with the intended algorithm and not any other arbitrary program? In this, I think that you also not only you have blind box to provide privacy, but I think you also have another product to certify whatever is inside the
Yeah. So we mostly talked about confidentiality of inputs that are sent to remote server, for instance, in both our cases. But then there is integrity. How do I know that they're doing what they say they would? And for instance, if I talk about TEEs, how do I know that, for instance, OpenAI uses secure enclaves? Because they can very well say they do, but they don't. In that case, you have no hardware isolation and it's exposed to the admin. Actually, there is a mechanism for that. And so imagine you want to use, I am OpenAI and you as a consumer. Before you send me any data, you ask me to prove that I'm using a secure enclave. And the idea is that there are low-level hardware APIs that enable to create a kind of certificate that says, here is a hash of the code that is loaded inside the enclave. And the whole thing is signed with a secret that is derived from the hardware that is tamper-proof and cannot be, which means that I, as OpenAI, cannot forge such signatures. And then I send that to, let's say, NVIDIA, who is the hardware provider, and they can verify that the signature is legit, as they have the list of the GPUs they sold and can verify that it's actually one of their signature. And if they do, they sign the whole thing, and then they send it back to you, and you use the public key of NVIDIA to ensure that you are taking to a secure enclave with the right code. At the end, you know two things. You know that you're talking to a secure enclave, and you know exactly the hash of the code that was loaded in the hardware. And therefore, if this code is public or audited, then you can know exactly what will happen on your data. In our case, our code is open source. So if people want to trust us, some hardcore people can look at our open source code, check if it's okay, compile the thing, look at the expected hash, and if in practice they see this hash when they start talking to our enclaves, then they know that they're talking to the right one. And this is server-side code integrity, which is something I don't know that in many examples we have that beyond blockchain, but this is a very strong property because this solves the issue of you as a company saying, okay, what will OpenAI do with my data? You have no way to know what they do with your data. As soon as you send it there, you don't know what happens. But with secure enclaves, at the cost of strengthening the hardware provider and the cloud provider, you not only have something that is fast and private, you also have visibility over what happens to your data. And based on that, then you can also compound that and create complex systems. For instance, you can say, today, I, as OpenAI, use this hash of code and this hash of data, and this created this hash of a model. And I can link everything and sign it with the hardware, and I can put that on a blockchain so that maybe next year, the White House will say, okay, what data did you actually use OpenAI? And I say, look, I can provide the cryptographic proof that is so on and so on. And so that's how it works.
Okay, thank you. I think that for FHE, maybe it's a tricky question because it's difficult to only with an FHE scheme to actually prove that you are executing a tricky program. But I'm aware that there is some work on verifiable computation applied to FHE. I don't know actually how mature it is. Yeah, I just wanted to ask your opinion on this.
Yeah, so again, with FHE, what you trust is the mathematics. So all the time that your data is encrypted, you're sure that it's not leaked. So you send to the cloud, you're a client, you send your data to the cloud. The cloud cannot decrypt your data. And even if they do malicious computation, they will never see your data. So they will send you maybe an answer that is incorrect, but they will never see your private data. So the data of the client that is encrypted stays private all the time. But of course, there are applications where we would like to verify that the cloud did the computation. So even if your data is not in danger, you would like the functionality to be assured. And as you said, yeah, there is lots of research going on in both zero knowledge proofs and verifiable computation in general for several applications. For zero knowledge proofs, what I see is that we have ways to produce the proofs. The proof can be verified very quickly. The size of the proof is reasonable. The problem is that generating this proof takes lots of time. And so research is doing lots in this direction in order to improve the production of the zero knowledge proofs. And yeah, I think we will see many things happening in the next few months here, especially with the blockchain also application coming into play, which requires zero knowledge proofs to verify computation. So yeah, I think, yeah.
Yeah, okay, thank you. Maybe for MPC, it is clear that you can get correctness if you apply a protocol that ensures active security. But when I go to literature to read privacy preserving machine learning based on MPC, the majority of the proposals I find are based on semi-honest model. So there seems to be like a practical community's acceptance of the semi-honest model for machine learning. Why is that if active security provides more guarantees?
Repeat the question?
Yeah, like there is like big amount of literature, many papers that proposed semi-honest protocols for machine learning. And active security is obviously better. It has more guarantees, it provides correctness as well. So why is so many people providing semi-honest protocols?
I don't think I have a particularly nice answer on that. Because it's like, you know, PPML is a field that sits like on the border of two fields. And, you know, like you have like, not everybody naturally has like the whole expertise. And I think if people are coming more from the ML side, I think that semi-honest protocols are just much easier to kind of grasp and like get into them. Whereas like of course you on the cryptographer side, like cryptographers are like very much into like active security, even better like full threshold and like through the whole sync edit with oblivious transfer and homomorphic encryption and whatnot. But on the other hand, then like you know like if you're mainly a cryptographer, like you might not be very interested in like getting into the depths of your ML algorithm. So that would be my observation. It's just like, yeah, it's complicated.
So it's basically that the machine learning guys are adopting semi-honest and cryptographers are adopting active security. It's more or less.
Yeah. But then the cryptographers are not necessarily like the ones who are very excited about, you know, machine learning algorithm X implemented in cryptography.
I always assumed that it was.
Yeah. So something quick about that is that I do think that in the cryptography community, specifically in MPC, we take things in a very modular way. So I don't think we think of semi-honest security as the end goal. I don't think we are in a setting where you get rejected or criticized if you have a semi-honest protocol. So people aim for that because it's a way, there is already many complications in the semi-honest setting. So I don't think we think of our protocols as if they are semi-honest, that's how they are, the state they are, they cannot be improved. It's more like this is the first step. It takes 2 hours, it takes 1 minute, whatever. This is the benchmark. Let's jump from it to active security. And in fact, in the honest majority setting, if you can ensure that a majority of the players are honest, we know techniques that can compile passive to active with very low overhead. Like depending on the computation, the overhead can be concretely very small, like less than twice the amount, like something like 50% more, 40% more, 30%. So I think based on these observations, in the dishonest majority setting, is definitely much more difficult to get active security, but it's not impossible. So people think of semi-honest as a first step. We don't know, I don't think we have a very good understanding of the applications, what the industry demands, what the world demands, what we need. So that's why the world is open. Like you can write a paper about anything you want, and then people can read it and make their own decisions based on the paper. So I think there is room for everything as of now because we don't know what's the standard.
Mhm. Okay. Okay, I have another question. In the previous tables, there were people talking about black box attacks on AI, like model extraction, model poisoning. There are techniques to detect and prevent that. But those techniques imply inspecting the client's input. You have to read the client's input and then try to detect the attack. But if we have private AI, we cannot see the client's input. So how can we conciliate both things, privacy and protecting the models? So any of you can actually try.
In the case of using secure enclaves, you can just say, okay, today I don't see the data, but I can say that this is the hash of the inputs, and I can log that. And if in the future you are suspicious that the attack has been done, you can ask, okay, as a client, show me the data linked to that hash. And that's one way. So when you do the inference, you don't know. But if at any time in the future you have suspicion, you can have a contract that says, okay, you're obligated to show data that you sent to the AI model. And that's how you can, balance both.
Okay.
Yeah, maybe I have a question to relaunch. How can you obligate the client to show you his data?
It's more of a contractual thing. Imagine, I don't know, it's a bank, I'm using OpenAI. You can maybe have a contract that says, okay, today, so the bank sends the data and OpenAI does not see the data. But the enclave can say, okay, today I saw that hash of the data and that produced whatever output, and I send the whole thing, and then you can store that proof wherever you want on a public blockchain, whatever. And then you can say, from a contractual, like organization to organization contract, say, okay, that's what was done today. And if, I don't know, like the FTC, whatever, comes and want to know whether you, as a bank, you are trying to steal the model of OpenAI, you can just tell them, okay, show me the data, show me, and then as an organization, if they are contractually bound or if they are being audited, then just show the, that's the reason why they would show the data.
You guys have any opinion on this?
Well, I would say in general, like if there's a detection algorithm, you can always run it within the black box. That's like certainly the case for MPC. And so the cool thing about MPC is like whatever is okay to be revealed can be revealed as part of the computation. So, if you can compute the bit that says like 0, 1, good or bad input, you can just reveal that to the computation party, so then can like act on it and refuse to do any further with this particular input.
Something quick also, there is an answer to that, which is the paper answer, which is it's orthogonal. So it's orthogonal. We don't care. And that's the typical sentence we write. And of course we do care, but I would say it's definitely a different domain knowledge that you need for that. And I think at this point, maybe it's a good opportunity to say one of the things I've seen in the PPML domain in general is that I think someone in the previous panel was mentioning that we see these two, it was Christian, that we have these two communities, the PPML workshops in the AI conferences, the PPM workshops in the crypto conferences. And I think it's all disjoint and people are doing things their own way. And I think, well, you can't imagine how many times I've written this sentence, like these input-output attacks, these things, go and read this list of 10 papers. And I think they are also similar references in the other domain. So I think we need more interactions to be able to have a more educated decision on how to defend against things and how to have a completely robust solution.
Just to follow up on that, I guess one way is to do it on the server side, so you don't deploy the model on the client side. Model deployed on the client side, even just by doing, a limited amount of requests. It's very hard to protect your IP once it's deployed on premise. And if you're on the server side, there's a defense called money. And calling OpenAI a lot of times to try to reverse engineer the model is very expensive. And that's one kind of way. Even though at the same time, what you see is that if we talk about LLMs, you don't need that many data points to actually have good models. So like a lot of new LLMs, like APAC and so on, they kind of scrapped OpenAI to get a good synthetic data set. And then they fine tune on that. So they don't directly have the model, but they have a good data set to have a model that's good on a specific task. And that's another way to steal a model, kind of. You still pay them though. You still pay like 10,000 data points you get from them. But yeah, and then you're autonomous after that.
Okay, money is a good protection there.
Maybe another observation to relaunch on what you said, and also what was said this morning, actually several times. It's that, cryptographers and people that do AI sometimes don't understand exactly what is going on the other side. Like cryptographers don't get the exact details of what is important in AI and so on. So I think that one thing we should, as cryptographers especially, try to develop, and which is missing, and we are starting to work on that, is tools that allow people that are non-experts in cryptography to be able to use the cryptography in a safe way and in an easy way. So develop tools that allow people to be able to use the technology easily, user-friendly tools. In homomorphic encryption, since I talk about it, as instance, it's very hard to set up the correct parameters to make the efficient computation. And it's very hard for cryptographers to do it. Imagine for people that will develop. It's not cryptographers that will develop applications in practice. It's going to be computer scientists or other developers, machine learning experts. So what we have to do as cryptographers, in my opinion, is provide those tools for them to be able to use the technology in the most efficient and secure way. And I think this is one of the main directions that are hoping for the future that will come.
And you are actually doing that, no? Because Zama has concrete. It's a very easy to use library. Also, Martel has MPSPs. I think you also include some libraries for machine learning in MPSPs framework, no? Okay, so
I mean, it includes functionality.
Some functionality.
That does machine learning stuff. It includes machine learning functionality.
In
I mean,
MPSPs.
I wouldn't claim it integrates particularly well. I mean, I've recently worked a bit on integrating PyTorch. But yeah, it's more like standing on itself.
Okay, and also Microsoft has blind box. So all of you actually have it's happening here. Amanda? All of you have a hands-on experience. You have done experimentation with concrete, with blind box, with MPSPs or other libraries. So could you tell us which is the biggest neural network that you have implemented and managed to make work in a useful time window, and how it does compare with an execution in the clear? So the difference in what the market requires and what the technology gives right now. Okay.
So in general, not only for my personal experience, but in FHE in general, what we can do. So if we talk about neural networks, we have to distinguish training and inference. Training, we can start doing things, but we can train very small neural networks for now, or fine-tune data on pre-trained neural networks. What we can do very good is inference effectively. Nowadays, what we can evaluate are most of the neural networks, some of the neural networks that were state-of-the-art like 5, 6 years ago. We have some CIFAR, MNIST, ResNet, generally not too deep, but yeah, even big neural networks. And the timings that we have is between a few seconds and a few minutes. It depends on the neural network. I'm talking about executing it on a cloud server like AWS that you can rent easily. But yeah, this is what we can do. Recent hot topics are trying to see what to do with LLMs. I mean, an LLM is huge. Also, executing it in clear, it's messy. But we're trying to execute part of the LLM homomorphically in order to, as I was saying before, protect the IP of the model. And there are some preliminary results that came out recently, and I look forward to the next months, years to see what is going to happen.
So
It's very promising.
if you have to tell, for example, a neural network to classify cipher 10, how long it lasts? Minutes?
Yes.
Minutes, okay. And
Seconds.
in MPC?
Are we
Active
talking
secu- active
inference
sec-
or training?
No, inference, active security, dishonest majority.
Dishonest majority. Oh, yeah, that would be like minutes, like at least. I mean, like for the nice results, you work with honest majority, and I think there you can see for 10 inference, like I would say seconds. So like it's I think sort of like the cost starts like I would say it starts around 100x, but it can also be 1000x or more. So the biggest, back to your original question, like the biggest one that sort of properly run is like MNIST with honest majority, and I've benchmarked CFR10, but I don't think I've ran CFR10 until a proper model, because every iteration costs the same, so you only need to run one iteration to have your paper result. Like that's it for inference. I think the latest result is that they have actually run a large language model at Alibaba Group, and they found that they can do one token in, was it 7 or 9 minutes?
Which one? So the GPT-2 is like 25 minutes per token?
Okay.
Two parties.
Okay. No, I think, okay, we might be talking about something else.
And the
Then,
Nano one is like 7 billion, and it's like 5 minutes per token.
yeah, I think I'm thinking about that one, yeah.
Okay, so but if I keep active security, but I go to honest majority, I think you have a really nice paper called Fantastic Four, in which, yes, both of you, in which you bridge the gap in efficiency between passive and active security by adding an extra party, like that would go even much faster. Like maybe you can run cipher 10 in seconds, in the order of seconds.
Yeah, I mean,
Yeah, I think this is
wouldn't put my life on it.
this is all again with an asterisk in it, because it depends on the network setting. So it's like we're assuming 4 parties that are well connected most of the time. It is like corruption 1, meaning that you have a 25% of corruptions at most. But there are all these different things. If you're willing to make these trade-offs and they're okay for your application, I would say, yeah, that's true. We can definitely make much faster things under these assumptions. So it's all, I think Marcel earlier commented, we have a lot of flexibility in the setting of MPC, because you can choose your poison in a way. Oh, you want to do the honest majority, you're willing to assume this, then it's fine. Some people say it's unrealistic, some people say it's realistic. I'm yet to find, show me a realistic setting where it fails, show me a realistic setting where it doesn't work. It's still like, we don't have this is not industry driven. It's not like the industry is claiming honest majority is the standard, active security is the standard. We are writing papers, we are writing our results, and then people who want to use it, they can choose the setting that better fits their application.
Okay, I think for this, probably the execution is comparable to the execution in the clear, and there is not so much overhead, right?
Yeah, exactly. You can see 2 approaches. So one is using secure enclaves, and yeah, we see from 0 to 50% slowdown in very extreme cases. And we're able to run as big as models as you have today on regular hardware. We have done examples with Bloom 175 billion, and it worked with 20% slowdown. And yeah, it's because it's hardware based, it's much faster. And this, as I said before, it comes at the cost of trusting the cloud provider. So this is something that we have to do, but it's much more plausible that it is deployed in the future. And it's not trivial either. For instance, if you have a model on several GPUs, you have each GPUs to attest each other. Then you also have to think about, how do I distribute the secret to several enclaves? How do I recover? And so on. So it's not trivial, but if done properly, secure enclaves can, in the future, power GPT-4 or GPT-3.5. We're going to deploy, for instance, a Llama 270B with secure enclaves. And so it's rather interesting. And the good thing is, yeah, it's very easy to use, very fast.
Yeah, I mean, it's clear that maybe TE is right now is the technology that can meet market requirements, and MPC and FHE still is evolving towards that, no? And I still don't know like how long it will take for MPC and FHE to catch up in terms of efficiency. But here goes a difficult one for you. Once MPC and FHE meet efficiency to be applied in the market, do you think the TEs will become obsolete, or they have any competitive advantage beyond the efficiency that they have now?
I don't know. It's to me like it's even 20% slower for someone like OpenAI is a pain in the ass. I mean, it's lots of. I mean, like even if the question is, do we think it will be as fast, as easy to use? I mean, literally the same speed between FHE, MPC, and regular computation. I don't think so. I think there will be maybe a gap. Maybe it will be 10 times slower. I don't know the gap, but with the scale of the application we talk to, 20% slower is sometimes it's a deal breaker. And I'm not even talking about all the other elements we need to have. For instance, like sometimes you just don't do like the simple matrix multiplication operator. Sometimes you have to do other things. For instance, if we go beyond the linear algebra only operations, there are other things that you need to have for service to be working, some database, some complex things, some operations that are not necessarily, linear algebra, and that can be maybe tricky for other, purely mathematical solutions to do. So I'm not saying that I don't see the applications, but there are so many factors, and based on that,
basically you are betting on them not catching up.
yes.
Okay. That's the bet. Okay. And now the reverse question for you guys, like what does it have to happen to catch up? Like what is the future direction, the challenge that you have to overcome to make MPC and FHE make these obsolete?
Maybe, yeah, I can start. So just to clarify, we can do all the functions. We can evaluate really everything, like from linear combinations to multiplications to lookup tables. So there's no real limitation on the things we can evaluate. It's true, we need to catch up. But there are, I would say, two big directions to catch up. The first one is, of course, research. Researchers are still proving that research advances. For now, what we see is mainly incremental results. So you have small factors of improvement, but still very interesting ones. But if you're looking for a really huge improvement factor, is hardware that we're looking for. And there are many companies, many projects that are developing, they're working on developing dedicated hardware for FHE. And what we expect is to have the first generation of dedicated FHE hardwares in 2025. And the factor of improvement that is expected is 1,000 to 10,000, depending on the application as well, which will reduce drastically the slowdown compared to the clear text, and which will make effectively FHE ready to use. Again, the question of we will replace TEE, we will not replace. I don't know if it will replace. I don't know if there's anything to be replaced or everything that will become obsolete. As I said before, like what we trust is mathematics. So mathematics is pretty solid in general. We don't need to trust the manufacturer. So this is a major point for FHE, but again, TE are extremely efficient. I don't think one will replace the other. I don't think any of the technologies we're describing will replace completely the other technologies. There are no a miracle solution, as my colleague Damian will say, for all the cases. What I think is that every one of the solutions that we're discussing here, the one we're not even discussing here, has different functionalities that will solve different problems on different scenarios. I don't know, FHE is very nice for inference, but is not nice for training at the moment. But MPC is great for training, so why not using it? Like why we should choose between the technologies? I think the best will be to use them more like combine them depending on the scenarios and not make a choice. So I don't think any of them will become obsolete, but I think FHE and MPC at some point will catch up, or definitely will catch up with TIE.
Yeah, and this is for you guys. For FHE is clear, like whenever I see people talking about future directions for FHE, they mention hardware acceleration. But in MPC, the bottleneck seems to be communication. No? So how do you solve that problem?
So MPC is definitely communication bounded, right? And I think unless we get to a point where communication becomes instant and the rules of like the rules of physics are not true anymore, then we won't be able to match certain bound. But I think it's very important to follow up on what was mentioned before. We don't need to catch up. Nobody needs to catch up with anybody. Like I think we offer different trade-offs. Every technique offers different trade-offs. And just like you have different programming languages, some of which are better for some things than others, I definitely think that FHE, MPC, NTEs, and all the other things offer different things that just cannot be compared. So I think while speeds-wise, like in terms of speeds, we won't be able to reach certain efficiency as other techniques. I think we have very strong security guarantees, like the strongest of all, if I may say, because we have the possibility of getting information theoretic security, assuming certain honest majority things. So we sort of move from trust the math, trust the assumption, trust LWE is not broken, trust LPN works, trust all this. We move to trust that 2 out of 3 parts are going to collude. So if you're okay with this, I think we definitely become very competitive. And a quick thing I wanted to add also, I don't think many of us are writing papers blindly. Like we move from 10 seconds to 9 seconds. We move from 6 seconds to 3. We move from 2 hours to 1 hour and a half. Who knows if the original 2 hours were already enough for some applications? Like, I think we need more applications from industry. We need more motivation on what is acceptable and what's not. We're just improving things by 20%, 30%, trying to make them slightly better to get our papers, which I think is very important. But I think we need more input from the real world to know exactly what's needed.
Yeah, I think you guys mentioned a valid point that actually I wanted to ask next, that is synergies. Like I see sometimes papers that they propose TEs to provide active security in MPC, or there is FHE in the pre-processing of MPC. There is also now a revolution in zero knowledge proofs. There are new techniques popping up continuously. So how do you see the synergies between all these technologies? How can we use them in combination?
Well, I think, the synergies between MPC and FHE, like, they're already very clear, because actually the most efficient two-party computation uses FHE already as a component. Like, I'm aware of some works that also take steps into integrating MPC and secure hardware. It's not something that I personally have worked with, so I can't comment well on that, but I would just really second Daniel's point, is like, the point that was generally made before, is that, there's the trade-offs between the technologies, and I think they're unlikely to go away. So it's always about, what's the best technology for a certain scenario. And like, as a sort of personal anecdote, like, ever since I've been in the field, I've been asked, or I've seen people taking sides between honest majority and dishonest majority and malicious security and active security. And sometimes I'm pressed, like, come on, like, won't you take a stand for, like, the gold standard, like active security with dishonest majority? Come on, like, everything else is just rubbish. And I'm like, no. And actually, that's why I created MP-Speed. So, like, you can just switch from one to another essentially in the blink of an eye, because you don't have to re-implement anything. You just choose another protocol, and then you're done.
Okay, thank you. I think we may ask the audience some questions, because we are running out of time. I have another one. So, so this is more personal. It's a topic that really interests me. Like, now in parallel to MPC, FHE, or AI, there are other technologies that are also evolving. One of these technologies is 6G. It's really a big revolution now. 6G will cover massive deployment of IoT devices. So we'll have like very small devices producing data continuously that will need to be smart. And the problem is that all the standards for communication in IoT are low bandwidth. So we'll have low data rates. Like the best standard can give us a few megabits per second. In FHE, for example, we don't have interactivity. We have ciphertext expansion. So we have small data, we encrypt, becomes big data. In MPC, we have interactivity. So probability is the only one that maybe doesn't have any problem with low bandwidth. But how can we make these technologies work in a scenario with low bandwidth like we will have for sure in the future? Maybe it's not possible.
Well, I think in the context of MPC, I can only like reiterate the client-server model. So I do not envision MPC being run sort of like at this edge devices, but I could well imagine like edge devices implementing some basic secret sharing and then using that to protect the data. Just basically that it sort of goes directly from the edge into the black box that MPC provides.
Basically do like outsourcing, you just secret share your data and you let other people do the computing.
Yeah. I think that's by far the most realistic scenario. Like even if your edge device is like more powerful, like your smartphone, I find it hard to imagine that the smartphone would actually participate in a larger protocol, so actually participate in a computation with like several rounds.
For FHE, there's actually a very easy solution, which is called transciphering. Transciphering means that you will send your data encrypted with another encryption scheme, like a symmetric encryption scheme, as instance, where the expansion factor is 101, that is. So what you will do is you will send once the secret key that you use to encrypt with, I don't know, let's take AES. You encrypt your data with AES, you take the secret key that you use in AES, you encrypt it with your homomorphic encryption scheme, and you send it once to the cloud. Now, what happens is that your secret key is there encrypted, is safe, and you send your data encrypted with AES, just to make an example. AES might not be the best solution, but just to use a use case. Now, what happens on the cloud is that when the data arrives, you decrypt it homomorphically, which means that you evaluate the decryption of AES homomorphically. And in practice, at the same time as you're decrypting AES, you're encrypting with homomorphic encryption. And then on the cloud, you can continue doing homomorphic computation. So your data is always encrypted. There's always a layer of encryption, which could be the symmetric encryption key, encryption scheme or the FHE. But in the end, you can do the computation on the cloud. So the communication is not a problem anymore. Of course, the downside is that you have more computation to do on the cloud because you have to decrypt AES on the fly.
At the end, you have to choose a symmetric cipher that has low multiplicative complexity for that to be efficient.
Yes and no, it depends. There are some schemes that want a low depth, multiplicative depth. There are some schemes like TFHE that don't care actually about the multiplicative depth. You do evaluation of lookup tables with the bootstrapping. And so again, AES might not be the best choice, but there are some stream ciphers that might be interesting. There was lots of work done on specific transciphering schemes for specific FHE schemes. So we don't use it much now, but it's a very promising field of research.
And I think just for ending, these do not have any overhead in terms of communication. So this is not a problem at all for your technology.
Yeah, we use regular, AES or whatever. I mean, there is no extra new, like, encryption scheme. We do modify TLS to take into account the verification of the enclave, as I mentioned, but the encryption itself is standard.
So it's completely ready to be implemented in massive IoT.
It could be, yeah. You still need to do the extra verification, okay. Not only, you do the regular TLS thing, but you have to also check, okay, am I talking to an enclave? So exactly what code is inside, like who signed it? Is it like NVIDIA? So it's very cost efficient. I mean, it doesn't take a lot to do verification like that on even a smartphone.
Okay, I think this is it. I would like to thank the panelists for all the insights. Thank you for coming. And for all your answers. So please, we can give an applause. It was very
Thank you so much. It was very. Oh.
And I learned things.
Sorry?
I learned